Alright, I'm going to show you some things about 3.11, linear approximation, and differentials. Okay. First thing is, linear approximation, we usually use capital L of x, and we're finding the L of x of a function at a particular x value. And the formula is L of x equals f of a plus f prime of a times x minus a. And what I want you to see, and you can pause it and write that, but what I want you to see is this is just the equation of a tangent line. So if you had a point, let's say the point was x comma f of a, and you wanted to find the slope at that particular spot, you know, all you'd have to do is figure out the derivative at that spot. So we would say that would be f prime of a. So if you wanted to write the equation of the tangent line, then you would use the point. So we would say y minus the y-coordinate, which in this case would be f of a. And then we'd say equals, and then the slope, which would be f prime of a. And then x minus whatever the x-coordinate is, in this case it's x minus a. And that's pretty much it. Now we just kind of put it in the form as same as L of x. So we'd say y equals, and I'm going to add the f of a over. So that would be f of a, and then plus f prime of a times x minus a. And then that's it there. The y we're just saying is L of x. If we say we're using an official linear approximation to predict, you know, other values that are really close to a. So then we would just replace the y with an L of x, and we have the exact same thing I had on the slide previously. Okay, so let's look at an example. So here what we have is we've got turkey, and turkey is in the oven. And we really don't know the function to describe the temperature of the turkey for any number of hours that it's in the oven. We've got a little bit of data, but no function. And the question for us is to try to figure out the temperature of the turkey after 3 hours. So we know at 0 time it's 50 degrees Fahrenheit, and then we know after 1 hour it's up to 93 degrees Fahrenheit. At 2 hours, it's up to 129 degrees Fahrenheit, and we're supposed to make some prediction as to what the temperature is at 3 hours or after 3 hours. So what we want to do is we want to figure out at least an approximation for the derivative at this particular spot, because we want to try to figure out the slope of the tangent line, which would be the derivative right there. So go like this. So the only thing we can do, we can't really find the derivative at that spot, but we can estimate using the two data points that are closest to it. So we're going to go ahead and figure that out. So we're going to say that f prime of 2 is approximately, we would subtract the y's over the x's, so 129, oh wow, that tool is a funky business. Okay. So this would be 129 minus 93, and then we would do 2 minus 1, and so we get a change of 36 degrees, and that's 36 degrees Fahrenheit per hour. That is the rate of change at that particular time. At least at a time period of 2 hours, the temperature is going up 36 degrees per hour. Okay, so we got our estimated derivative, and now we need a point, and you know that we already have the point, so we use the point 2 comma 129, and then we just write the equation of the tangent line. So we say y minus, and the y-coordinate is 129, and we have the slope, which is 36, and we have x, really. So then we have x minus 2. And we can kind of write this in a better form so that we can actually use it to make the prediction at 3 hours. So we have y minus 129 equals 36x minus 72. And then we'll add the 129 over there. So when we add the 129, we should get 36, I believe. No, just kidding. Let's see. We get, let's see, 129. Hold on 1 second. So we get, yeah, we get 57. So we get 57, if we care to put it in this form, it doesn't really matter, so plus 57. And then now you could say that this is L of x, and we could use it to predict what the temperature is after 3 hours. So we'd say L of 3, and we plug in 3 for the x. And we get approximately, what would we get? 36 times 3 plus 57. We should get about 165 degrees Fahrenheit. Okay? Now, the other thing we want to do is we want to be able to identify whether this would be an underestimate or an overestimate. So it depends on what the curve is doing. So if you notice that the curve is, doing this here, where it's increasing but at a decreasing rate, we could say it's concave down even. Then we're going to say that our estimate is looking like, since we're using a linear approximation, it looks like our estimate is probably an overestimate because it was already starting to level out. So most likely this is an overestimate. Okay, make a little note, overestimate. Okay, next example. Let's say we want to find the linearization L of x of the function at a. And so what we're going to need to be able to do this is we're going to need the derivative. So f prime of x is 1 over x. And we're going to need the slope at that spot. So we're going to go ahead and just plug in a 1. So f prime of 1 equals 1 over 1, which is 1. So we got a good slope. And we're going to actually need a point as well. And you guys probably know if we were to plug in a 1 into this function, it looks like this. This is the natural log. And so if you were to plug in, just write it here, y equals natural log of x. If you were to plug in a 1, you would get a 0. So our point that we're looking at, the point is 1, comma 0. So we've got a point, we've got a slope, and now we just write the equation of the tangent line. So we're going to say, let's see, this would be y minus 0 equals 1, and then x minus 1. So if we simplify this a little bit, it would be y equals x minus 1. So if you wanted to write this, with the L of x, then you would say that your L of x is x minus 1. So what we're saying is that the line y equals x minus 1 is a really good approximation. As long as you're really close to 1, you can go ahead and use this linear approximation to find other values really close to that. So sometimes it might be easier to use a linear approximation instead of the function itself. Okay? All right, so let's try to use our linear approximation to figure out what Ln of 1.08 is. So we would say, hey, what's L of 1.08? And we would take that and just plug it in for the x. So that would be 1.08 minus 1, and that gives us 0.08. How close is that to what the actual answer is? Well, we could use a calculator and we could figure out what natural log of 1.08 is. And it turns out when you use a calculator, I'm just making a note that if you use a calc to figure out natural log of 1.08, then it's approximately, it's 0.07696, which is obviously, very similar. Okay. All right, now the third question with this same problem is we're going to need the calculator. So it's going to say this. It says, determine the values of x for which the linear approximation is accurate to within 0.1. So remember, this is a linear approximation. It's not the same thing as the function. They are different. So, but we want to figure out how different are they. So if you wanted to be accurate to within 0.1, when you're looking at the x value of a equals 1, how close to 1 you basically need to be to have this work out. So what you'll do is you'll take the function and the linear approximation, and you'll subtract them to see kind of what the distance is between them, and you put absolute value bars, and that guarantees that you're going to be figuring out the distance. So you subtract the two, and then you say, since you're wanting to be within 0.1, then you say you have to be less than 0.1. And you can actually use your calculator for this. So the left side you can say is y sub 1, and the right side is y sub 2. And you can just graph this and try to figure out when is the graph of y sub 1, when is that lower than the graph of y sub 2, because that's when it would be less than here. So all I'm going to do is I'm going to graph the left side on the calculator, the right side on the calculator, try to figure out exactly when the left side is lower than the right side. So let me show you with the calculator. Okay, so I plugged in the first one, the left side, into y1, and then plugged in the right side into y sub 2. And then the window that I chose for this is kind of dinking around with it. It's 0, 2, and then the y min and y max are 0 and 1. When you graph it, it looks like that. And we basically need to figure out where does that intersect and where does that intersect. And then we would say, hey, all this space here is where the x values would be, that would be the answer we're looking for. So you would go second, calc, and you would go to intersect, and you just want to figure out, and you go first curve, second curve, just press enter, and then you get 0.616, you remember that. Actually it's 0.617 if you round it to 3 decimal places, and then you go over to the other one. When you want to do the intersection over there, you just kind of move the blinking dot so it's a little bit closer to where you're looking. So you move it a little closer over there, press enter, press enter, press enter. Gives you 1.516. So those are your answers. So in between those two. Okay? So I'm going to go back and write those answers down. So let's see what we got. So our answers for this are that x needs to be, let's see, x needs to be within, it needs to be bigger than 6.17, and it needs to be less than 1.516. So I'm going to circle that. Alright, let's go to our next problem. Alright, find the linearization for f of x equals sine x at a equals 0. So, of course, to do this, you're going to need the derivative. So, let me find that. So, f prime of x would be equal to cosine of x. And we're going to need to figure out the derivative at that spot, the slope at that spot. So, f prime of 0 equals cosine of 0. And so we would say that equals 1. So we've got a good slope. So here's our slope. And we need a point. So we're going to plug in 0 into the function given. So we're going to say, hey, what's sine of 0? And of course that's 0. So I should say what's f of 0. So our point is 0, 0. Sorry, number 1 is not working. So 0, 0, we got a slope, and so we're ready to write the equation of the tangent line. So we would say y minus the 0 equals the slope, which is 1, and then x minus the 0. So all this would be is y equals x. And so if we want to write it in our linearization form, then we would say that L of x equals x. So it's interesting because we're saying that when you're really close to 0, that sine x and x, the functions, are pretty much the same thing. They're so close. So this one here, sine x, and this one here. And that's kind of interesting. It kind of reminds me of a theorem. And it says this. You remember, let's see if we remember this. So remember limit as x approaches 0. So when we're really close to 0, sine x over x equals 1. Okay? And that's because sine x and x are so similar, so when you divide them, you actually end up with 1. Alright, now last topic is differentials, and this deals with the different pieces of the tangent line, kind of the different portions. So I'll let you get this picture down, and I'll kind of be describing it as you write it down. So the blue is the function. So the blue is f of x, let's say, some function. And the black is the tangent line. So let me make a note that the black is the tangent line. And you know, the tangent line is going to be broken up into pieces, and we're going to have one piece that runs along, you know, this part here, and that's the dx. We call it dx, or we call it the change in x. These are actually going to be the same. And then for the other part, we have the change in y. This is the part that the curve actually rises or falls, the curve itself. And then the dy is the amount that our tangent line actually goes up and down when we move over a certain amount of x. So the dy and the change in y are going to be different because we know our tangent line is not exactly the same as what the curve does. So that'll be different, but the dy and the dx and the change in x are the same. Okay. I think that's all I want to say there, and actually get to an example. All right. Compute the change in y equal and dy and sketch the graph. Okay, so first thing we have to do is we have to figure out the derivative. So we're just going to find the derivative. So we're just going to say dy dx equals, and that's 2x. And you can actually split up your dy and your dx. So you can multiply both sides by dx. So you'd have 2x dx. And then you're basically going to go ahead and plug in a 1 for the x. So we plug in a 1 for the x. And then when they give you the change in x, that's actually the same thing as the dx. So dx is also 0.5. So you're able to just plug in your numbers. So that's 2. And then for the x, we're plugging in the 1. And then the dx, we're putting in 0.5. So dy equals, we multiply those together. So dy is actually 1. Okay. So what in the world does that represent? So we'll try to get a decent, somewhat of a decent graph of this. So let's say we start off, we know that the curve is y equals x squared. And we know that when you plug in a 1, you get a 1. So we know that. And then let's see what else here. So then we're talking about moving over a little bit, 0.5 to the right. So that means we're looking right here at 1.5. So we're kind of, let's see, how do I do this? So first of all, we draw a tangent line at 1. That's where we're finding the slope, right at 1. And when we move over to 0.5, we're looking to see how much the linearization went up when we move over 0.5. So we want to figure out, hey, this would be the dy, this part, when we move over 0.5. So let's be right in. And then you'll notice there's a little bit of a difference between the dy and this right here, because this, all the blue, would be actually the change in the curve. So the blue would be the change in the y, and the red would be how much the linearization went up. So they're different. So again, the red is just this much, and the blue is a little bit more. So we found out that the dy is equal to 1, but there's actually a little bit more of a difference in the curve. The curve goes up a little bit more. So if you wanted to figure out exactly how much that is, I think the easiest way to do it is maybe to plug in 1.5, because you're right here at 1.5. Go ahead and plug in 1.5 into the curve. So let's figure out what that would be. So we'd say y equals 1.5, and we would have to square it. So 1.5 squared, what is that? That should be 2.25. So we can compare that with what we had when we plugged in a 1, because we're basically seeing what the difference is in the distance here. So when we plugged in a 1, we figured out, let's see, if we plug in a 1, then it would be 1 squared, so that's 1. So you can tell there's a difference there of 1.25. That right there is the change in y. So change in y equals 1.25. And we see that the linearization is only 1. So kind of makes sense there, hopefully, for you. All right, last example. Find the differential dy and evaluate it for given values of x and dx. So this one's very straightforward. What you're going to do is just figure out the derivative again. It's really similar to the last one. So dy dx equals 3. And then we're going to say, except we're going to use the chain rule. So x squared plus, well, maybe that's x squared plus 3, reduce that by 1, and then multiply by the derivative on the inside. So 2x. And then we're going to isolate the differential dy. So we have, let's say that would be, well, same thing. And that would be squared, and then times 2x, and then we would multiply by the dx, so we have dx there. And really we're ready to just plug in all the numbers. So we would say the differential would be equal to 3, and then our x in this case is 1, and our dx is 0.05. So we're going to plug in a 1, square it. We're going to have 2 times 1, and then the dx is 0.05. And so our answer here, the differential, is equal to 10.8. And again, that's just how much the tangent line was able to rise when it went from 1 to 1.05. So it went over just a little bit, and it rose up 10.8. This next slide is kind of a picture of the situation. So I'll let you kind of take a peek at that. But we went from 1 and then we went to 1.05, and what we just found out was this, the 10.8, and we could actually figure out how much it rose, and that would be the change in y. And it's more, it should be more. So what I did was I plugged in a 1 into the original function, I got 216. Then I plugged in a 1.05 and I got 227.26. And I subtracted those two values, those two differences, you know, the two y values, and I got 11.26. So that 11.26 is actually the change in y, and it's obviously different than the dy. So 11.26. All right. So that's really it as far as differentials and linear approximation.